The homework is due on Monday. The homework is for this is not due on Monday. This is back when we were going to do section 1-3 yesterday and today. So we'll just have to kind of wait until we see how long this takes us. All right, so section 1-3 is titled New Functions from Old Functions. We're going to talk about transformations today. All sorts of different transformations. All different possibilities of transformations. So let's just jump right in. All right, by applying certain transformations to the graph of a given function, we can obtain the graphs of related functions. These are, we're going to talk all different types of transformations. We're going to talk about rigid transformations. We're talking about non-rigid transformations. We're going to talk about shifts, stretches, compressions, all those good stuff. All that good stuff, okay? So, and we're going to use some notation that we could apply to any different type of function. We talked about all the different types of functions in section 1-2. And these transformations can apply to any of those different types of functions. So let's start most basic. These are the shifts, the translations. And I like this diagram that the book gives down below. That's why I kind of screen captured it in there. We can't see the bottom one there, but write whatever you need to here, okay? Some of you guys are like, I know how to transform a function. We've been doing this at Algebra 2, Mr. Lammer. We've done it so many times. But some of you are like, I still don't understand this. Okay, so let me explain it from the beginning. To move a function up or down, okay, to move a function up or down, whatever the function may be, to vertically shift a function, you add or subtract out on the outside of the function, okay? You're changing the y-coordinate of the function. You're changing the f of x value, so it's going to be like f of x plus c. Whatever the whole function is, I'm going to add a certain amount to it to make it move up. And I'm going to subtract a certain amount to it to move it, make it move down. Okay, so f of x plus c is going to shift upward. F of x minus c is going to make it shift downward. Now, if I take that and I put that plus or minus sign on the inside, so I'm changing the input value of the variable. I'm changing, instead of just x, it's now x plus or minus c. That's what's going to make it move left or right. And remember that the horizontal stuff is the weird stuff. It's kind of like the counterintuitive stuff. It's the ones that kind of do the opposite of what you think it should do. So if I'm going to move it to the right, you're going to see a minus amount. If you're going to move it to the left, you're going to see a plus amount on the inside. Minus actually means right. Plus actually means left. And again, then I'm changing the input value of the variable. Okay. So this is a good diagram of what you see here. Again, you could print this page out in the notes. I post all the PDFs. So if you ever need to like print them all out, if you want to have them as like one sheet, go for it. You can do that. But here's what we have. Again, plus c is going to move it up or down. Plus or minus c is going to move it up or down on the outside of the f of x. Plus or minus c is going to move it left or right on the inside. So this is a f of x plus c. Sorry, f of x plus c. This is an f of x minus c. Remember, c, both inside. This is actually moving it left because it's a plus, right because it's a minus. Plus or minus on the outside, more straightforward. I go plus is up, minus goes down. So the outside, f of x plus c or minus c, sitting on the outside is going to shift it up or down. The f of x minus c on the inside is going to shift it left or right. Again, you have to kind of think of it as changing the input value or changing the whole function. Okay, I'm going to talk about those two different ways. Changing the input value is something horizontal. Changing the output value or changing the whole function is something vertical. Okay? Changing the input value is something horizontal. Changing the output value is something vertical, which makes sense. If I change the input is x. X means horizontal. I'm going to change something horizontally. If I change the output value is y. That means I'm going to change something vertically. Same thing is true for the reflections. I'm just going to jump to the rules. Okay? These are the stretches and compressions too, actually. We kind of took these as its own, like this was one rule for us back in Algebra 2. This was one rule for us back in Algebra 2. Those were the horizontal stretches and compressions and the vertical stretches and compressions. We kind of just like made it one rule. Like for example here, c times f of x. C times f of x. C times f of x is our vertical stretch or compression. They write it as a different rule if it's a compression. They call it shrink, by the way. I'm probably going to use the term compression, but they use the term shrink. But a vertical stretch or compression, that is C times f of x. I think back in Algebra 2, we used A times f of x, whatever. Something multiplied to the outside of a function is a vertical stretch or compression. And now we're switching from adding and subtracting to multiplying, right? Multiplication is going to be some sort of stretch or compression. So C times f of x, vertical stretch or compression. Notice that I'm doing it to the whole function. I'm doing it to the outside of C. That means something vertical is happening. And then I'm going to shift down to the next two. Those are the horizontal stretches and compressions. Now, again, it's going to be counterintuitive. You know, we said minus was left minus was right and plus was left. Now what I'm going to say for horizontal stretch and compression is that it's actually the reciprocal. You know, interestingly enough, it was the additive inverse when talking about the shifts. It's the multiplicative inverse when we're talking about the stretches and compressions. So it's the reciprocal of that value that's going to go inside. And again, it's going inside because it's horizontal. I'm changing the input value because it is horizontal. So if I have a horizontal stretch by 2, reciprocal of 2 is 1/2. 1/2 x is going to go in. If I have a horizontal compression by 1/3, and again, I'm saying compression instead of shrink. Horizontal compression by 1/3, reciprocal of 1/3 is 3, so it'd be 3 times x going in as my input value. And then here are the rules about the reflecting over the y-axis and reflecting over the x-axis. It's always the opposite one that you change. Like, for example, if I say reflect across the x-axis, you're going to change the y value. If I say reflect across the y-axis, you're going to change the x value. So reflecting across the x-axis is going to be negative y, negative f of x, negative of the whole function. If I say I'm going to reflect across the y-axis, well, then I'm going to take f of negative x. The input value is going to change, which makes sense because think about the reflection over the x-axis. The x-axis is the horizontal line. So if I'm reflecting across the x-axis, I'm changing the verticality of it. And if I'm changing the verticality of it, that's changing the y value, negative f of x. If I think about reflecting over the y-axis, my vertical axis, well, then I'm going to flip it left to right, which means I'm changing the horizontalness of it. Okay. I'm making up those words. Again, I got that diagram down below. You can see it. You can print it out for you if you'd like it. But again, all of these are up on Canvas if you'd like to kind of compile them for yourselves. If you need to brush up on any one of those, if you need to refer back to them, they are in your book. So honestly, those transformations will apply to every different type of function. You want to stretch a polynomial, a vertical stretch a polynomial, multiply it by a constant on the outside. You want to vertically stretch a trigonometric. You want to vertically stretch sine, multiply it by the outside of sine or cosine, right? Vertically stretching the trigonometrics. If I want to reflect a rational, reflect it over the y-axis, okay, go in everywhere you see x and make it a negative x. It'll do that. Okay, these rules will apply to any type of function that we learned in section 1, 2. I kind of talked about it for the trigonometrics. This is I liked these diagrams. Like this is just my parent cosine. Right, the middle one, that one is my parent cosine. This is cosine 2x, and this is 1/2 cosine x. Notice that multiplying on the outside is going to vertically stretch or shrink it. When I was really bored in high school, I would go. No, none of you are going to do this in my class. I would go sine x, 2 sine x, 4 sine x, 6 sine x, and 8 sine x. Oh, no. 8 sine, oh, that's apps. That's apps, get back there. Sine x, right? Zoom 6. Oh, I still got some data on there. But I just think it looks so cool. Because look at what it's doing. It keeps vertically stretching it out and out and out and out as the number gets bigger and bigger and bigger. And then what you can do is like, oh.
You put 2
Yeah,
I put, whoa. Well, that's sine x squared. Okay. Whatever. I digress. All right, but you get the idea, right? Vertically stretching it out. This is horizontally stretching it, right? I am just kind of increasing the period of it each time and multiplying by the inside of something. Okay, let's take a look here. Given the graph of the square root of x, use the transformations to graph the square root of x minus 2, the square root of x minus 2, negative square root of x, 2 square root of x, and x, the square root of negative x. So I'm just going to graph each one of these in different colors. Let's start with, oh, you know what? Let's start with our parent. Let's put our parent in black. Okay, if it's the square root of x, I can do 0, 0, right? This is not the plus or minus the square root of x. This is just the square root of x. If I take the square root of 1, I get 1. If I take the square root of 4, I get 2. If I take the square root of 9, I get 3. So here is my parent. Oops, should be a little bit more careful. The square root of x. Okay, there is my parent. Okay, what's my first transformation going to do? Down 2. Okay. It's going to take everything and shift it down 2 units. All of these coordinates are going to go. Oh, come on. Blue, please. Blue, please. You do. There you go. Okay. Do we see it's just shifting down 2 units? That parent function shifted down 2 units. What's this going to do? Right. Yeah. Be careful with that. You see minus, you think, ooh, left. No. That's actually to the right 2. Let's put this one in red. That's a right 2. Okay, this is going to get a little crowded in here. Right 2, right 2, right 2. Off the graph 1. That's okay. What's this one going to do that I've underlined in green? Yeah, it's a reflection because I see a negative, right? And since it's on the outside, I'm changing the y value. That means it's a reflection across the x-axis. Okay, so I'm going to take my parent function and reflect it across the x-axis. So this point's going to stay the same. This black point's going to actually be right on top of that other blue point. 2 units here, 2 units here, 3 units here, 3 units here. Just get a nice, clean reflection over to the other side. What is that going to do? Vertical stretch by 2, right? So every y value, I'm going to multiply by 2. I'm going to take all those black points and I'm going to multiply by 2. Well, 0, 0 is going to stay 0, 0. 1, 1 is going to go 1, 2. 4, 2 is going to be 4, 4. Right? Yeah. And then 9, 3 is going to be 9, 6. And then our last one here. What's this one? Maybe I'll put it in yellow. What's that one going to do? Yeah, y-axis. Reflect across the y-axis. So that point down here is not going to change. This origin point is not going to change. 1 unit here, 1 unit here. Okay, it looks like I've got 4 on the other side. So 4, 2, and then 9, 3, just on the opposite side. A couple key things to point out. If you got a point that runs through the origin, the only thing that will move it away is a shift, right? If I stretch or compress it at all, that point on the origin stays exactly the same. Same thing with a reflection. Okay? Same thing with a reflection. Let's take a look at this one. Sketch the graph of the function f of x is equal to x squared plus 6x plus 10. Now, I am going to actually do this in a unique way. I bet your first instinct is probably to do negative b over 2a. Find the axis of symmetry and find the vertex and do that whole funky stuff, which is totally fine. Totally fine. Taking a look here, if you tried to find the zeros, they would not exist. Why? Because if I take b squared minus 4ac, 36 minus 4 times 1 times 10, that's 36 minus 40. It gives me a negative number. So that means that this does not cross the x-axis. Those zeros would be non-real. So I'm actually going to do this in a very specific way. I'm actually going to write this into vertex form. Okay, I'm going to take this x squared plus 6x plus 10, and I'm going to rewrite it in vertex form. This is something that we did in Algebra 2. You guys hated it, but we did it. We're going to take that function and rewrite it in vertex form. And how are we going to do that? We're going to actually complete the square to do that. What do I mean by that? Well, the nice thing about this is that there's no coefficient on x squared. Because if there's a coefficient on x squared, you can't really complete the square. I mean, there's ways around that, but it's a little bit more difficult. I'm going to partition off x squared plus 6x, and then I'm going to leave 10 kind of like on the outside of parentheses. What completes my square on the inside of the parentheses? What do I add to complete my square? 9. Good. Okay, good. Remember how to complete the square. Remember, take half of b and then squared. So half of 6 is 3, squared is 9. So I'm going to plus 9 right here. Okay, so what do I have to do on the outside? I can subtract 9. Yeah, watch out, subtract 9. Remember, we added 9 to the right side. We would normally think, well, if I add 9 to the right side, I got to add 9 to the left side. But I can't, because that's an f of x. So I'm going to subtract 9 over here. Got to balance that out. Okay, how does that help us? Well, that makes this factorable. So f of x is equal to x plus 3 squared, and then plus 1. And now that it's in vertex form, we can see the transformations, can't we? What is this plus 3 telling us to do to the parent? Left 3. What's that plus 1? Up 1. So left 3, up 1. Left 3, up 1. And then from there, you can kind of think of it this way. Like, there's my new, come on, give me a different color. There is my new origin, right? There's my vertex. Was there any sort of stretch or compression that had happened? No, because we would see it as a multiplication on the outside or inside of the parentheses there. So there's no vertical or horizontal stretch or compression at all. So I know that if I go right 1, it's up 1, right 2, up 4, right 3, up 9. 1, 2, 3, 4, 5, 6, 7, 8, up there. And then those are all reflections. How do I know that that's going to happen? Because think about the parent. I square 1, I get 1. I square 2, I get 4. I square 3, I get 9. Right? 2 units here. I got to be careful there. 3 units here. 3 units here. Okay. And there's my graph. Now, could I go old school and do negative b over 2a? Sure. Negative b over 2a. 6 divided by 2 times 1. So 6 divided by 2 times 1 is 3. And it's negative. So the axis of symmetry is at negative 3. Okay, that confirms that. I could plug that in to find the vertex. If I plug in negative 3, I probably get 1. Because that's what I see it as right now. Something else I see, no pun intended, something else I see, the c value, the y-intercept is 10, right? Didn't it fall right on 10? Okay. See, all of these things are kind of, tie in together. The next one, I know we have to graph some trigonometric ones. Let's save that for Monday.
That sounds good to you guys?
Yes, sounds good to me. That'll be a nice treat Monday morning. Come in and graph some trigonometric functions.